If you recall, yesterday we set up a couple of double integrals for the volume under the circular paraboloid 4 minus x squared minus y squared, and above the semicircle x squared plus y squared equals 4 in quadrants 1 and 4. So above the semicircle. And we did this in the standard way, the thing that we do with all integration. We're doing multiplication. We're doing multiplication where we take the height times the area, and we're going to evaluate that at all the points we care about. So the region R is just a description of what's x between and what's y between. So this region R was described by what's x between and what's y between. That's how we describe the region R. And so we came up with two different double integrals. One was a dx dy integral, where y went from -2 to 2. When y is going from -2 to 2, x is going from 0 to the plus square root of 4 minus y squared. And then we integrated the function 4 minus x squared minus y squared. This was the height above the xy plane. So this is what we're treating as the height, 4 minus x squared minus y squared. And this was set up as a dx dy integral. So the integral is asking us what we have encoded in this integral is take this height and multiply by this area for all these x values, and then for all these y values. And then we also set up a double integral with x values, or a double integral dy dx. Where we first listed what y is between. And here y goes for this generic x value, y goes from the top of the circle to the bottom of the circle, or from the bottom of the circle to the top of the circle. So the negative square root of 4 minus x squared to the positive square root of 4 minus x squared. And x was between 0 and 2. We do this for all the x between 0 and 2. We did half of an integral. We ran into some trigonometric substitution, and I had to resist the urge to do some more trigonometric substitution. And we found that it looks like this is equal to 4 pi. If our calculations from yesterday were correct, this volume was equal to 4 pi. Getting the volume, of course, was the least important part of the problem. We could have just looked up what this volume was. I'm sure someone has done this problem before. Knowing that the volume is 4 pi, not the issue. Setting up the double integral, understanding height above the xy plane, what's x between, what's y between, that was the point of the problem. So here's what we want to do today. So we set up the volume as a double integral the volume was set up as a double integral of height times area. And once we wrote our area as dx times dy or dy times dx, we set the volume at, we wrote the volume as height times length times width. Nothing fancy here. We're just using our just the idea of what volume is. Volume is some height, some length, and some width. This three-dimensional space that we're taking up. So even though we set our integral up as height times area, what it boiled down to once we started doing the calculation was height times length times width. The same thing that we always do when we want to calculate a volume. Height times length times width. Because our cross-sectional area had the same shape, we got to get away with doing it this way. So notice that our three measurements, our height, our length, and our width, it looks like they came from different places. The height was the function, and then the length and the width were what's x between and what's y between. So it looks like our height, length, and width kind of had different ideas. Length and width were what's x between and what's y between, but height was the height of the function above the xy plane. But that's just asking what's z between. So even though we measured the height with the function is just telling us what z is between. So in the context of this problem, this height fell into the same category of length and width. This is just what's z between. So we had set our volume up as a double integral. Height times area. Area is just length times width. The way that length and width showed up in this problem was the dx and the dy. The height was given by the function. But when we say the height is given by the function, we're just saying how far above 0 it is. So we're just saying that z is going between 0 and the function. Any questions? We want to see that all we're doing is saying what's x between, what's y between, what's z between. If all of these things are constant, we just call it that distance. If the length is always between 0 and 2, we just say the length is 2. And if it's a rectangular box, if we say the width is always between -2 and 2, we just say the width is 4, that distance, because it's always the same. And then if the height is from 0 to 4, then we just say the height is 4, because z is everything between 0 and 4. And then that would give us a rectangular box of 2 times 4 times 4, whatever that is. 32. Also useful, 32. And so if we got a value here that was more than 32, since this shape is clearly going to fit in the box from 0 to 2 on x, -2 to 2 on y, and from 0 to 4 on z, if we got something that was more than 32, we know we are wrong. So the point is that even though we set up this double integral, we're integrating this function dy dx, and we're interpreting the problem as volume, we're still just saying what's x between, what's y between, what's z between. It's just that we did what's z between in a slightly different fashion, which brings us to the thing that we want to look at today. Which is triple integrals. I like to do this now after we do the double integral example, because then I could recycle the same example. So efficient. Lazy is correct. It's funny that we use lazy as kind of like a derogatory. We say, oh, that's just lazy. Unless we like the person, in which case we just say, wow, they're efficient. I mean, it's like, oh, fuck you, English. The whole point of humans should be to do less work. There's so many of us. Why do we all have to work so fucking hard? Ridiculous. It's ridiculous that on one hand, we say, ah, look at this efficiency. Efficiency comes from not wanting to do too much work. And if we don't like what's going on, then we call that lazy. But if we do like what's going on, then we call it efficient. It's like, make up your mind. Are we trying to save calories or are we not? So lazy is correct. I will take that 100%. I didn't want to have to come up with another example. Because, I mean, look how much work it took us to get us just a 4 pi that we put into a machine. Ugh. Let's save some calories and just recycle. Let's call it reuse. We all know that recycling is a lie. Triple integrals. So in a triple integral, the thinking is going to be the same. Instead of just a double integral, we'll have a triple integral. We'll be integrating some function, f of x, y, and z, over some solid w. We don't get to use s. Later on, we're going to use s for surface. So by the time, so we had to trade this one out. So we're just going to call it w for solid, because of all the w's that show up in the word solid. Now, in this case, we're going to be integrating over dv. So dv is going to be some small rectangular piece, rectangular solid piece of w. We're integrating a function x, y, and z of x, y, and z. W is going to be just the set of x, y, and z that we want to plug into the function. So w is a solid. It's a bunch of x, y, and z. The rectangular box or piece. V is for dv for d volume. Just like before in a double integral, we had dA, where R is a bunch of xy. R is a bunch of xy. It's all the xy that we're plugging into f of xy dA. dA was a small piece of the region R. So dA dA was a small rectangle in region R. W and dV are going to take the same rolls. W is going to be a bunch of X, Y, Z, a solid in three-dimensional space, a solid in R3, and dV will be a small rectangular solid in a small rectangular box, let's say, in the solid W. Just like dA was a small piece of the region R, dV is a small piece of the solid W. A little cube. As long as we stipulate that the sides don't have to be all the same size, it's a little cube. So this bunch of X, Y, Z, these are the X, Y, Z's that we're going to be plugging into the expression f of X, Y, Z times dV to get us whatever we're trying to calculate. And we're going to so the integral part is describing what values we need to plug into our function times dV. So this is a bunch of X, Y, Z that we plug into the function X, Y, the f of X, Y, Z. That's what we're going to be plugging into the f of X, Y, Z times dV. So that's where we're describing what we plug in to our f of X, Y, Z dV. And we do it the same way we did with the double integral. We say what's X between, what's Y between, and what's Z between. And this little rectangular cube in W called dV, it's going to have three factors: a dx, a dy, and a dz. Just like dA was dx times dy. What that means is that we could describe the volume that we looked at yesterday, the volume under at 4 minus x squared minus y squared and above this semicircle in the xy plane. We could have described that volume using a triple integral. I could have said x goes from 0 to 2. Y goes from negative square root to positive square root. And then I could just have another integral for what's z between. And z starts off at the xy plane where z is equal to 0 and goes up to the function. So z goes from 0 to the function 4 minus x squared minus y squared. This is set up as a dx, dy, dz. Now, if I want this triple integral to represent the volume of the solid, if we want the size of the set over which we are integrating, we just integrate the function 1, the unitless function 1. If we want the size of the set over which we are integrating, we integrate the unitless function 1. Let's just make this even more generic. Just let the function of x, the function of x and y, or the function of x, y, and z, like we have in this case, just let the function be 1. With no units. Find the size of the set over which you are integrating, integrate the unitless function 1. Wanted the area of the semicircle, I would, instead of integrating the height of the function, I would integrate just 1 with no units. Then I would get meters from the dx, meters from the dy. Total would be square meters times 1 with no units. To get the volume, I had meters from the dx, meters from the dy, and meters from the height of the function. The same thing is happening down here in this triple integral. I'm getting meters from dz, meters from dy, meters from dx, and 1 has no units. The reason that we want to point this out is that we want to remember that integration is for multiplication. So if we want to know what we can use integration for, we just have to think about how we use multiplication. So for example, one of the things that might happen in this particular solid, maybe this solid has a constant density of, let's say, 1 mass per unit volume. In which case, I've got meters from dz, meters from dy, meters from dx, and kilograms per cubic meter from my 1 represented as a density. The meters from my cubic meters from my density cancel out my cubic meters from the dV, and I'm left with kilograms. Applications of integration are just applications of multiplication. You want to know what to do with integration? What can you do with multiplication? Look at all the shit that we do with multiplication. Just look at those factors and make one of them continuously variable, and now we're integrating. Make one of the factors continuously variable, because that's the big thing about calculus. A lot of times, too often, we describe calculus as the mathematics of change, but it's not that. It's the mathematics of continuous change. The weird stuff happens because we're trying to create a model for continuous change. We're trying to create a model for continuous change. And the models that we built started by looking at discrete change. we break things into chunks. And we do this all the time in lots of places. Calculus is all over the place. If you look at a dance that was put together, when you build the dance may have been built by breaking it down into steps. We take discrete steps where you do a bunch of small things, and then you put them all together and it becomes a continuum. When you're learning a song, you learn the verses. You break the song into verses, chorus, bridge. You learn the verses, the chorus, the bridge. And maybe while you're learning the verse, you break that down into lines. Once you learn the parts, once you broke it down into discrete parts, you put it all together into the continuum of the song. Whatever units you have for Z, whatever Z represents, those units will be right here. Here are your Y units, whatever they are. Here are your X units, whatever they are. Here are your function units, whatever they are. Our favorite one to use for this volume one is think of the volume. Describe the volume with the integral and describe, let's say, a variable density. Let's suppose that this weird basis for a peacemaker helmet is some kind of shape, and it's made with variable density, and we can describe that density at each different point x, y, z. To find the mass of the solid, I would integrate the density of the solid with respect to the volume. So at each point x, y, z, I calculate the volume, the mass, by taking the density times the volume at all those little points, then add them up. The same thing that we always do with integration. Any questions? So double integrals, we were like, oh, what's x between and what's y between? For a triple integral, we just keep going. What's x between, what's y between, what's z between? Same thing. If we have a function of 4 variables, dx1, dx2, dx3, and dx4, it would be a d, I don't know, super V. You just draw a fancier V. So however many variables we need to describe the situation. Now, at that point, it's going to be very hard for us to picture what's going on, because I can't just go meters, 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 because that's 4 meters to the 4th. And if my function is also meters, then I have meters to the 5th. Ugh, now we can't picture it. Or even if we can, maybe we have a very distinct picture of what it looks like in 4 dimensions in our minds, but we can't communicate that to other people. How frustrating must that be? Any questions? The reason that we do things like area is equal to length times width is because it's very convenient for us. But that's just standing in for any multiplication that we want to do. The reason that we use height times area is because it's convenient for us to do. But we can use any product of a one-dimensional thing times a two-dimensional thing. How's everybody okay? Probably good that the physics department doesn't watch me when I start grabbing from physics texts. It's like, oh, look, there's physics doing a multiplication. I'm going to grab this. I'm going to make one of these factors continuously variable. And the physicists and engineers are like, oh, dude, that's not how it works. I'm like, well, it is now, because this is a math problem. And all we need to do is make something continuously variable. We just want to multiply where one of our factors is continuously variable. Integration is how we deal with that. How's everybody okay? Everybody looks so sad. Because we went from double integrals to triple integral. You just multiplied integration by 1.5. And you're going to try to do that with one page of notes with one triple integral shoved down here into the corner of this whole page. What the hell, man? But yeah, because it's the thinking that I care about today. You know what I mean? All the tests are doing the stuff that you're never going to do again. Maybe that's why we have to have that on the tests. You know what I mean? I remember when you took a test and you had to do a trigonometric substitution. By the way, I distinctly remember the trigonometric substitution I had to do on my Calc 2 test. I got to the theta integral and it was a substitution integral. And I said, son of a bitch, the only reason I'm fucking doing trigonometric substitution is because it said in problem 4, do trigonometric substitution. And I looked at the integral, I'm like, oh, fuck you. This is a substitution integral. But they're like, oh, no, no, no. What case is it? Well, it's sine case because it was like a 4 minus x squared. So it was like super obvious. But there was a 4 minus x squared, and then there was an x sitting right there. I'm like, well, why not I just do a substitution? You know what I mean? We ask weird questions on tests for math, and then we never care. And then later on, when I start talking about what is integration, everybody's like, well, add 1 to the exponent, divide by the new exponent. Well, that's functionally what it means, but what does integration represent? Calc 2? You know what I mean? But what I want is that integration is multiplication where one of the factors is continuously variable. You can't leave anything out. That's about as efficiently, the efficient way to say it. You've got to say continuously variable, not just variable. Because if it's just variable, we could say addition. 3 plus 4 plus 5. We're just using addition. That's different than 4 plus 4 plus 4. That's where we get to use multiplication. But on the interval from 0 to 3, add up the function 4 minus x squared. Now we've got an integration problem. Because 4 minus x squared is continuously changing. How's everybody okay? Yesterday, by the way, was the day of 4 minus something squared because that was different from trig. Because yesterday we integrated 4 minus x squared in Calc 1. And I said the same shit that I did at 12 that I did at 8. All right. So triple integrals. What's x between? What's y between? What's z between? Super predictable. All we have to do now is come up with other ways for describing x, y, and z. Right now we're describing x, y, and z with locations. And what we saw was that using rectangular coordinates for round things is decidedly inconvenient because trigonometric substitution shows up. Until I did an end run around the trigonometric substitution, it's like, oh, haha, I've got a calculator. All right. So now all we need to do is learn some more sets of coordinates. But that's going to be for another day. That's going to do it for today. I will see you all on tomorrow. Everybody have a good day, and thanks for playing. Have a good day.